lecturing on curves, which are, of course, varieties of dimension 1. And in this context, a lot of the difficult, deep questions are more arithmetic. I mean, the geometry, as we'll see in today's lecture, is pretty much simple and well worked out, well understood, so that all the subtleties and difficulties are more in the arithmetic. So the theory requires perhaps a more arithmetic as opposed to geometric flavor when we focus our attention on one-dimensional varieties over, of course, non-algebraically closed fields. So I'm going to give today a kind of general overview to the things I'll be talking about, sort of present you the general picture of the arithmetic of curves. So I'd like these talks to be reasonably informal, so if you want to ask questions, please feel free to interrupt me and slow me down, and I'll try to answer them. In exchange, though, so I'd like to be open to questions while I'm lecturing, so to pause occasionally, and especially if you feel confused, and then you should slow me down. And in exchange, though, I have sort of in my lectures packed 1 hour of material in each lecture, so I'll ask for your indulgence if at some points I have to run a little bit overtime past the 1 hour mark if I've had to take time to answer questions in the course of my lectures. Okay. So the basic object that we're interested in, of course, in this entire summer school are Diophantine equations. And these, as you all know, are systems of polynomial equations in any number of variables. So an exponent to xn equals 0. And traditionally, if we're number theorists, we're interested in the case where the polynomials fj have integer coefficients. So they belong to the polynomial ring with coefficients in z. And of course, the most basic question we can ask is sort of, if I call x the system of equations, we're interested in the system of the solutions to the equation, the set of elements in Zn satisfying the system x. Now, it's actually, if you want to be a little bit more modern, we can replace the ring of integers by any ring of integers of a finite extension of the rationals, or even more, a ring of S integers where we invert a finite set of primes. So I'm going to, one gains a lot of flexibility, actually, and one doesn't really make the question much more difficult. In fact, in some sense, one simplifies it by considering more general systems of equations where one replaces z by some ring of S integers. So O could be typically OKS, where so K is a number field, S is a finite set of places, finite set of primes. So finite here is crucial for many things. And OKS denotes the ring of S integers, so the elements which are integral over K, except possibly at the primes dividing S. Okay, and so we want to study now maybe this kind of solutions, which we can interpret as the set of ring homomorphisms from the ring of functions O of capital X into the ring O, where O of X is the coordinate ring O of x1 up to xn, modulo the ideal generated by f1 up to fn. So we're sort of interested in studying this solution set as maybe one allows perhaps the ring of coordinates to vary over all finite extensions of the rationals, and maybe one allows also S to vary in some way. So this system of equations represents the affine case, where we study sort of simultaneous systems of polynomial equations. We can also So this, what I described here on this board is sort of the case of affine equations. We can also consider the projective equations, projective case, where we suppose that all FIs, all these polynomials, are homogeneous, are sums of polynomials of the same total degree. And then, in that case, it's customary to write for x of k the set. I mean, so then this system of equations has an obvious solution, which is the tuple consisting of the 0 solution. We exclude that one from consideration, and we look at the set of elements x1 up to xn with coordinates in the number field k, but so satisfying this equation, modulo the natural action of k star. I mean, if we take any solution and we scale it by a non-zero element of k, we get another solution, and so we want to kind of identify two solutions that differ in this way. And you see that when one defines rational solutions like that, one sees that essentially there's no distinction to be made between integral and rational solutions of such an equation, because if you have a rational solution, you can always scale it by something so that all its entries are integral. So sort of clear denominators. And so so when one writes in this projective case, one notes that x of k is equal to x to the solutions with entries in OK, or to solutions with entries in any ring of S integers. So in other words, integral and rational points correspond to the same Diophantine question. It's really the same thing. But I want to emphasize that the basic object that we're interested in, that we want to study, are integral solutions to Diophantine equations. When I'm in the affine case, I'm generally looking for integral solutions. And in the projective case, the study of integral solutions to this kind of equation amounts to studying the rational solutions to the dehomogenized version, where you set one of the variables equal to 1, essentially. Okay. So that's a way of unifying, in a sense, the study of integral and rational points, which a priori might seem like they have a different flavor. Okay, so the mandate I have in this series of lectures is to study the simplest, in some sense, non-trivial case of Diophantine equations from an arithmetic point of view, which correspond to the varieties of dimension 1. So, and those are called curves. So a curve is a variety over, let me just say over k for now, k being a number field, defined by these equations like this, for which, say, the set x of c, the set of complex solutions to the equation, is a one-dimensional complex manifold. Okay? Is one-dimensional. Well, this is kind of a naive sort of definition of what I mean by an algebraic curve. So, but in the zero-dimensional case, the Diophantine equation would just be a finite collection of points, so sort of determining solutions and so on is a kind of trivial question. It's in the one-dimensional setting that the question becomes interesting for the first time. But, okay, so I start by defining a curve to be a variety over k, but it'll be frequently useful. In fact, if I want to talk about the integral points, I have to have given myself a collection of equations with integral coefficients, which amounts to fixing a model for the algebraic curve as a scheme over the spectrum of the ring of integers. Okay, so we also we suppose, I mean, I'll be doing frequently in my lectures, we suppose that x comes equipped with a model, which I'll maybe denote by script x, over the spectrum of O being this ring of S integers of a number field k, so allowing us to talk, or to talk about, to define the set of S integral points, which are kind of viewed as sections of this curve over spec OS, OKS. So what are the basic questions we can ask about these equations? So so maybe perhaps the most basic kind of question is a qualitative one about whether a given curve has finitely or infinitely many solutions. So is x of OKS finite or infinite? You could ask for this kind of basic result. The second is if the following: if the cardinality of this set of solutions is finite, if you succeed in proving that it's finite, you might ask to give upper bounds on its cardinality. In terms of the equation X, the set S, and the field K. But you can also ask for more things. I mean, obviously, when we look at Diophantine equations, any solution comes with a natural notion of size, which is, roughly speaking, the amount of space you need to write the solution down, with sort of a kind of notion of arithmetic complexity. Those are encoded in what are called height functions, which you're not going to be hearing that much about height functions in my lecture series, but you probably will hear about them in some of the other lectures in this summer school. So roughly speaking, a height function is a function from the set of S integral solutions to the curve to the positive reals. There are various ways of defining it, but the feeling of a height function is always that it's meant to measure the amount of, so if you wanted to store a solution, say, on a computer, sort of the amount of memory you would need to do that, to store it in exact form. That's roughly what a height function is, a logarithmic height function in this case. And okay, so we can define these things which give a measure of the size, and then we can be a little bit more ambitious in the kind of questions we ask. But for example, if the cardinality of x of OKS is infinite, well, these height functions are cooked up, of course, precisely so that the set of solutions of bounded height is, for trivial reasons, always a finite set. I mean, you can only, in a given amount of computer space, you can only store so many solutions. So if this is infinite, you can sort of consider a counting function. So you might want to understand the asymptotics of the counting function, which I'm going to call nxb, which is the set, the number of points in X of OKS whose height is less than b. And you want to maybe know how that grows as a function of b. If the cardinality of X, O, K, S is finite, then you might want to understand say something about the maximum of the height of P as P ranges over this finite set. Now, this question might look a little bit similar to that one, but in fact, it's very different. It's actually much harder and more subtle problem. This kind of a good answer to this kind of question leads to an effective procedure, an algorithm for computing the set of solutions. Since then, if you know an a priori upper bound for the solutions, you just have to range over until you reach that point. Whereas this question here only asks for the number of solutions without specifying how far out they might be, and it's sort of a much weaker. We'll see that when we discuss in the next 2 days the proof of Falting's theorem. And okay, then a question which is maybe closely related to 4 in some sense is to give algorithms, effective methods to compute x of OKS. And these actually correspond to very fundamental theoretical questions in the subject. I mean, I know that in this summer school there's also a kind of emphasis on practical methods to compute solutions in practice, but also from a theoretical point of view, one is very interested in having results that say that one can actually at least in principle, effectively determine a set of solutions to an algebraic equation. This question is a fundamental one already in the case of curves, as we'll see shortly. Now, the answers to all these questions, so the basic fact, which probably many of you already know, is that all these basic questions, Can people see here if I put the board at this level? Can everyone see in the back? Yeah. Okay. Yeah. So as many of you probably already know, the answer to these questions depends a lot on the sort of the topological appearance. Of the set of complex solutions to the curves. Now, if you look at the set of complex solutions, let's assume that the curve is smooth. Okay, so assume that x is smooth, it has no singularities. Then x of c is, smooth in the generic fiber, so has a variety over k. So it has no singularities, and then the set of complex points is identified, at least topologically, also analytically, with some Riemann surface of genus G with a number of points removed, with a finite number of points removed. So it looks like SG minus P1 up to PS, where G is the genus, so SG is a surface, compact surface of genus G, where I've removed the S points. So here's the picture for G equals 3 and S equals 4. So I have this surface with 4 punctures and 3 holes. Okay, so that's the kind of topological appearance of any. So obviously when you pass from an equation to this, you squeeze out 2 integral invariants. You've obviously lost a lot of information about what the equation is. You can package further these 2 invariants into a single number, which is called the Euler characteristic of x, which depends only on this kind of topological appearance, and which is defined by 2 minus 2g minus s, minus the number of deleted points. So this is the number which governs the sort of qualitative behavior of the solutions to the curve equation. That's what I'm going to explain now. So the answers to these 5 basic questions which I've asked here are really governed by this quantity. Let me try to. Absolutely. Yeah, but that's a crucial point. I mean, because I've placed myself in the context where I only talk about integral points, and so the equation is very different, right? When you remove a point, then you're looking at a completely different equation. See if this will become a little bit clearer now when I discuss the three cases. I mean, it's not yeah. I mean. So what happens? So here are the three basic cases. The case where the Euler characteristic of x is strictly positive, which is the simplest case from a Diophantine point of view. Well, that corresponds to two situations. There are two possible situations, right? If chi is strictly positive, then obviously g has to be equal to 0, and this can be either 0 or 1. Those are the two. Those are the two cases, and then we have the following theorem. Is okay? So the theorem is the following three things are equivalent. So I have now an x, and I want to understand the integral. Actually, let me just assume here. Let me assume now that s equals 0. Okay, so I'm only going to talk about the projective case. So that in the projective case, there's no, as I said before, there's no difference between integral and rational points, and it's customary then to talk about rational points on curves, although it's not really, it's just a matter of terminology. So then I look at x of k. And okay, so the first condition is that x of k is non-empty. The second condition is that x is isomorphic to the projective line over k as a curve over k. And the third condition is that x of kv is non-empty for all completions, for all places. So for all completions kv of k, both Archimedean and non-Archimedean. Okay, so this is a theorem that you might have already heard last week, I guess, I would imagine, in some of the lectures on rational or close to rational varieties that you had in the first week.
How can removing a finite number of points can change the whole behavior of a rational point?
Well, of integral points. So in a few minutes, I'll give you an exercise which I will answer the question. Okay, so just bear with me for a few minutes. It'll become clear in. The following are equivalent. Sorry, yeah, I thought this was yeah. Okay. Yeah. So just bear with me, and I will explain that. So okay. So I mean, okay. This one, the implication 1 implies 2, is the Riemann-Roch theorem. It's a nice, it's a simple application of the Riemann-Roch theorem. Namely, so if you have a rational point on x of k, let's call it infinity. Then you can consider the space of the vector space of functions that have at most a pole at infinity, and that's two-dimensional by the Riemann-Roch theorem. And then you just choose a non-constant function in there, call that phi, and that gives you an identification of x with p1. So that's the Riemann-Roch. So then 2 implies 3 is clear, I mean, it's obvious. And 3 implies 1, which is the most interesting part, is the Hasse-Minkowski theorem, which is the local global principle for conics. That's the local global principle for conics. So if your curve of genus 0 has a point locally everywhere, then it has necessarily a global rational point. So this result somehow tells us that, in a sense, curves of genus 0 are completely well understood, and I'm going to be saying basically nothing about them in my lectures. Yes?
Is there no analogous statement for s equals to 1? It's not generally known, but not true.
Yeah, so for s equals 1, yeah, so for s equals 1, in some sense, the situation is even easier in a sense, because now you've marked a point, and so now, okay, basically, in that case, when s equals 1, x is isomorphic to the affine line A1. Okay? And now remember that I'm studying integral points, right? So this is the affine line over the spectrum of O. So the coordinate ring of x is just, in this case, O of x is just the polynomial ring in one variable over O. Okay? So an integral solution to this equation, so maybe this actually already answers the question that you asked. An integral solution to this equation, these solutions are indexed by elements of O. Okay? So x of O, in this case, when s equals 1, is identified with O. Whereas when s is not equal to 1, when s equals 0, for the projective line, we see that x of O, so this is for g equals 0, s equals 1, and for g equals 0, s equals 0, and the case where x is isomorphic to P1, then x of O is isomorphic to K. It's in bijection with K. Well, these mean just in bijection as sets. So you can see that there are a lot more integral points on P1 than there are on A1. Okay? So removing this point actually placed a strong constraint on the integral points. Okay? So that's just the way that the definitions are made. Okay, so anyway, I'm not going to be saying anything more about the case of strictly positive Euler characteristic, but I just want to mention now that what you've heard about in the first week, and you'll be hearing also in other lectures in the coming weeks, in the higher dimensional setting, trying to generalize this sort of very basic classical result for curves leads to a very rich picture for higher dimensional varieties. So we still have a lot to understand about the rational points on higher dimensional varieties which are either rational or close to being rational, questions like the ones I raised before on the asymptotics of the counting functions and so on and so forth. So this sort of simplest case, of course, when you pass to higher dimensions, everything becomes much more complicated and challenging, and that case which is completely worked out in dimension 1 becomes very rich and interesting in higher dimensions. Okay. But I really want to focus, actually, in my lecture, since this is completely simple and worked out, I'm going to be focusing on the case of Euler characteristic 0 and the Euler characteristic strictly negative. Okay, so now let me say a few things about the case of 0 Euler characteristic. So let's now look at the case where chi of x is equal to 0. So here there are really two genuinely different interesting cases. So G can be either 0, so let me just say it this way. GS, the pair GS, can be either 0, 2 or 1, 0. This I'm going to call the affine case because it corresponds to an affine equation, right? I mean, where I've removed some points. And this I'm going to call the projective case. In this case, the complex points looks like a Riemann sphere with 2 punctures. And in this case, it looks like a torus. And what can we say about those cases? So if X of O is non-empty, then X has the structure of a group scheme over O. So, I mean, it's like an algebraic group, but in the category of schemes over spec O. What it means concretely is that if you have two solutions over O, or over any finite flat extension of O, any ring of integers of a finite extension of K, a ring of S integers, then you can combine those two solutions to produce a third one via a natural algebraic group law, kind of algebraic group law. And in this first case, in the affine case, X is identified. So you need this non-empty assumption, of course, because the empty set is not a group. And you you choose a point in this setting and decree that point should be the identity. And once you've made that decision, then you've kind of pinned down your algebraic group structure on X of O. So in the affine case, X over O is isomorphic to the multiplicative group over spec O, over this ring of S integers. And in the projective case, so in the affine case, you see there's really only one model, somehow. Well, not quite actually. But this is not. Yeah, I'm assuming that these are non-singular, and yeah.
Like you have to some kind of minimum, to make sure that it's a group scheme. Maybe the sections are always for the group.
You mean under some special fibers? If I make some strange blow-ups, yeah.
Yeah.
Yeah, and yes, and there's another problem that I'm thinking of, which is that I could have a twisted form, right? It could be that the deleted points are not defined over. So even over spec K, what I say is not true, right? Because I could have. I could twist.
Well, but that's not a non-twisted.
No, yeah, but I'm saying. So this is not. I'm not saying that all X over O are this.
Okay.
I don't want to go into these kind of classification problems. I just said that this is sort of a typical example of the kind of structure that one encounters when one tries to study this. Let's just leave it at that. In the projective case, X over O will look like an elliptic curve. Will be an elliptic curve over spec O. And again, here, I could be allowing some singular fibers, but let me assume that the curve is smooth over spec O, so that all the special fibers are also, all the reductions modulo the primes of O are smooth curves over the finite fields. So they have no singularities, either the generic fiber or the special fibers.
So X is the thing over O, not over K.
Yes, so that's what I said at the beginning, that I kind of assume that implicitly in all that I say, in order even to talk about integral points, I need to give myself a model. And the model I'm giving myself here even is a smooth, proper model over spec O. Okay. So, in these cases, we have the following basic result. So, theorem that X of O is finitely generated in the affine case, this is just essentially the Dirichlet theorem on units or S units. In this case, you see it well because if X is GM, then X of O is just the ring, the multiplicative group, right? And we know that the group of S units of a number field is a finitely generated abelian group. And in the projective case, this is the Mordell-Weil theorem. That X of O, Mordell-Weil groups of elliptic curves are finitely generated. Okay, so I'll say maybe a few things about that next week when I discuss elliptic curves. But yeah, in keeping with sort of the general philosophy of this summer school that you start with the difficult things first and then go down to the easy things. I'm going to be talking first about chi strictly negative in the first week, and then I'll focus more on curves of genus 1 and elliptic curves in the second week of my lectures, so the third week in school. Okay, so now I want to say some things about chi of x strictly negative. Okay, so here, the basic theorem in that subject, the theorem of Siegel and Faltings, that when chi of x is strictly negative, then the set of integral points x of O is finite. The beautiful result, which is very simple to state, not so simple to prove. So if chi of x is strictly negative, then x of O is finite. Is a finite set. So the affine case, this is a theorem of Siegel. So it was proved. Let me just illustrate that by giving you the first interesting case of that theorem, and the main case, actually. I mean, you can reduce almost everything, the entire theorem, to this case, which is the case where x is the projective line minus 3 points, which I can take to be 0, 1, infinity, over spec O. So the affine case, I mean that S is non-zero. S is non-zero, yeah, exactly. So it just means that I've deleted some points so that I can choose an affine model over spec O. The first interesting case is the case where x is p1 minus 3 points. In that case, let me just work that out a little bit for you. I mean, in that case, what is x of O? What is the coordinate ring O of x? Well, that's just the ring of polynomials in the variable x. But you see, you've deleted, so x is a function which has only a pole at infinity. So I'm taking this standard function which has only a pole at infinity on P1. But I also have deleted 0 and 1. So I allow functions that blow up at 0 and 1, that have poles at 0 and 1. So the coordinate rings looks like O of x, 1 over x, 1 over x minus 1. And so that's my ring of functions, O of x. But now x of O is identified with the algebra homomorphisms from O of x to O. So the ways that I can specialize my variable. Well, but then to give such a homomorphism, I just have to specify what x goes to. But x had better go to something which is invertible, since then I have to send 1 over x to the inverse, which has to be an O. And also x minus 1 has to be invertible, since this guy has to go to the inverse of x minus 1. So you can see that, so if I take an f in this Helms, then f of x belongs to O star, and 1 minus f of x also belongs to O star. And this, so this number, this unit, it's a solution to the S unit equation. For the So integral points on P1 minus 3 points correspond to solutions to this well-known equation, the S-unit equation, which, and we know that that's one of the basic consequences of Siegel's theorem, that there are finitely many solutions to the S-unit equation. Okay, that's the affine case. And then the projective case, the case where x is a projective curve, was proven much later, and that's the celebrated theorem of Faltings. So what I'll be doing in the next 2 lectures is to explain the highlights, the main ingredients that go into the proof of this result. So that's my goal on the lectures of Tuesday and Wednesday, to kind of give you a feeling for the strategy that is followed in Falting's proof. But in the time, so in the time remaining, I would like to just say some basic things about curves. And in fact, well, even before that, I want to say a few things about the simpler case, which I claimed was completely easy and worked out, which are the case of dimension 0. So let me start by making a few comments about zero-dimensional varieties or zero-dimensional schemes over spec O. So dimension 0. So it's too, of course, a single equation, a single scheme of dimension 0 is too simple from a Diophantine point of view, but we can still consider collections of all those, and the questions about classifying all the totality of schemes of dimension 0 over spec O are very interesting. Those lead to some of the very interesting still open problems in number theory. So a zero-dimensional scheme essentially corresponds to a finitely generated O algebra. So I'm going to consider those. And I say that an O algebra R is, so I'm going to consider only finite algebras. And I'll also consider only flat, so finite flat, which I'll abbreviate to FF, if R is a finitely generated O module. As an O module, it's finitely generated, and free. It's finitely generated O module, free O module. So as a module, it's just a certain number of, finite number of copies of O, equipped with a multiplication. Okay, and then I say that it's étal over spec O if the quotient R mod X is reduced. It's a reduced algebra. In other words, it has no nilpotent elements for all ideals X in spec O. So if the quotients by all prime ideals is reduced, has no nilpotence. And we can consider the set, which I'll denote SHA OD, of all isomorphism classes of finite flat étal algebras over O of rank D. So I fix the rank to be D. Okay, and so now I want to state the classical result of Hermite, which is going to be useful in a number of proofs that I'll be giving later, which tells us that this set, so these are, you can think of as sort of the collection of the zero-dimensional schemes which in the generic fiber have D points, but are smooth over spec O. Okay, so that's the geometric picture you can have in mind. And the basic theorem of Hermite is that there are only finitely many of those. So that's a sort of the kind of maybe most basic finite result of algebraic number theory, which is going to be sort of the starting point for many of the results that we have on curves. So SHA OD. So here I remind you again that O is again the ring of S integers of a number field, a finite extension, and D is some rank. So I look at all these finite étal algebras of rank D over spec O, and this is finite. The cardinality is finite. And sort of give you the idea of the proof or the sketch of the proof. So given an element R, an isomorphism class in SHA OD, we can consider the field obtained by, so the generic fiber of this variety, the function field of, so O tilde tensored over, sorry, what am I, R tensored over O with the fraction field of O, which is K. And so this is a K algebra. Of degree D, which is unramified outside the finite set S of places. Okay? That's unramified because of this condition that the algebra should be étale, that this quotient should be reduced algebras for all ideals of OKS. And so then the idea of the proof is Hermite is to bound the discriminant. So one can bound the discriminant of K. And so, one can bound first the primes that appear in the discriminant. Those are only the primes in S at most. And then one can also bound the multiplicities. And then the next stage of the proof is to show that there can only be finitely many number fields with bounded degree and discriminant. Yes.
Sorry to interrupt. It seems to me that it all might be a consequence of finite flat. Is that not true?
No. For example, take. I can even give you something which is finite flat, but not even generically étale. For example, if I take O of x modulo x squared, okay, that's a nice algebra of rank 2. As an O module, it's just 2 copies of O. Okay. But who? You asked the question. Yeah, sorry. Yeah, so it's sort of 2 copies of O, but it has nilpotent elements. So étale is much stronger. So you don't want nilpotent not only in generic fiber, so when you tensor with K, but also when you reduce modulo various ideals. You don't want to acquire nilpotence. And if you look at what that means that basically if you kind of take that it's possible to find a good defining equation at every prime outside of S for which the equation doesn't have multiple roots. And that's sort of equivalent to this. So the more classical way that you might, if you're more of an algebraic number theorist than a geometer, you would have heard this theorem stated as the statement that there are only finite many number fields of bounded degree and discriminants, and it's an elementary thing to work out the two. Yeah.
You require flat homogeneity.
Yeah, that's part of flat. That's just, the meaning of flat in this context. Okay, so this is just a definition. I say that it's finite flat if it's a finite generated Fourier module. Okay, I didn't give you the independent. If you know it, good. Otherwise, don't worry. Yes, one can bound discriminant, of course, of L over K. Yeah, of that relative extension. And then and then one can show one shows. There are finitely many fields of bounded degree and discriminant. Okay. And that finiteness result is going to be very useful to us in tomorrow's lecture, actually. Oh, when I say the word place? Okay, so you're asking about why. Why do I say S is finite?
What are those places?
Oh, I've just given myself a finite set. Okay, I could allow this set to vary eventually, but the kind of basis, when I talk about integral points, I don't just want to talk about points with coordinates in the ring of integers of a finite extension of the rationals, but I also want to allow myself denominators eventually, but the denominators I can allow are kind of bounded by the primes. I give myself a finite set of primes and I invert those primes. So then the OKS is what's called the ring of S integers. They're elements whose denominators involves only the primes in S. Okay, so part of my data is this base, this ring O, and O is the set of elements.
So this is independent of the algebra R?
Yeah, no. S depends on O. See this O, this ring O? So I'm classifying finite flat extensions of O, but O was just an abbreviation, so maybe I should have made this, well. Here in this theorem of Hermite, O is the ring of S integers of a number field. Okay, this is not a general result, of course. I mean, if I inverted infinitely many primes, for example, it would cease to be true. Or if I put here, for example, K instead of O, this would be completely false. Right? I mean, then you'd be classifying field extensions or products of field extensions of degree D of a field, of which there are infinitely many. But working over this base kind of puts a restriction on the discriminant, and that's exactly the point. Okay. Okay. So, fine. Now I just want to say one last thing before I end. I want to make a remark. Yes. So R is up to, right, I mean, so it's an isomorphism class as O algebras, as algebras over O. Okay, and then I take this R. Oh, you're saying if I tensor with yeah, well, no, not in this context, right? Not in no, maybe. No, it could. You're right. That's. Yeah, exactly. Maybe not, actually. Maybe not. It could not. Yeah, but this assignment for passing from the scheme to its generic fiber is finite to 1. Yeah, so there's a little sleight of hand there. I mean. Okay. It's not hard to see, actually. It's finite to 1. Okay. So in the time remaining, I want to just say a little, sort of a very useful fact, actually, relatively elementary, about unramified coverings and the relation of the behavior of rational points between curves that are related by an unramified map. So I want to talk about unramified coverings and their sort of arithmetic applications. So I say that a finite morphism pi from a curve x to a curve y. So these are still over spec O. So remember that I had this integral model floating around. So I'm going to call these unramified only if the generic fiber is unramified. Only if the map is unramified in the generic fiber. So over so I'll say that it's called or rather I will call it is called by me. So this is maybe not completely standard terminology, unramified, okay? If the induced map of Riemann surfaces from x of c to y of c is unramified, for some embedding of O into C. So I just choose a complex embedding of the base, and I require that the resulting covering map of Riemann surfaces be unramified. And actually, if it's unramified for one embedding, it's going to be true for all. Yeah, so it sort of means that on the generic fiber, the morphism is unramified. Now, I want to state a useful lemma. So whenever you have two curves that are related in this way, you can ask sort of what is the relation between the rational, or the integral points rather, on one and the other. And it turns out that one can say something interesting, or useful at least, useful lemma. And the useful lemma is the following. So if pi from x to y is unramified in this sense, then there exists a finite extension L of k and a finite set S prime of primes or places of L actually containing S, or rather containing all the primes of L above S, such that the set of S integral points, so I'm interested in kind of understanding the set of S integral points over K of Y, of this curve which is in the image. And the point is that that is contained in the set of S integral points of S prime integral points over L of S for some for some finite L and some finite S prime. And the key point is that this extension does not depend. I mean, so from that you get all the solutions to Y over L, all the S integral points, to Y over K, are kind of dominated by points in this finite extension and Okay, so so let me give you the proof of that. Okay, so yeah, I mean, so this is a bit of a kind of abuse of a, so I'm identifying S with a set of places of L above S. So let me call that maybe S tilde. I don't want to make it too heavy, but so places of L above S. Yeah. Okay. So are there any questions about this? Maybe, I mean, okay. If you're a bit confused about the statement, I hope the proof will clarify what I mean. So, okay. So I'm going to, so the first fact, so the proof of this result begins with the following fact. So I have this, so if pi from x to y is unramified in the sense that I stated before, sort of on the generic fiber, then there exists a finite set, then there exists an S prime containing S, maybe, or that I can take to be containing S prime being a finite set of places, such that pi from x to y, so I look at these models over the base OS prime, the set of S integers of K, of S prime integers of K. So I've inverted now the primes in this possibly larger set S prime. So this is étal in the usual sense, in the stronger sense, étal not just on the generic fiber, but on all the special fibers. Well, that's sort of an elementary fact, because the condition for being étal, for the cover to be étal, is basically the condition of non-vanishing of a certain discriminant of a defining equation for the covering. Okay, so the condition of being generically étal is that this discriminant is non-zero. It's not a zero, which is a number. I mean, it's non-zero. And then you just take S prime to be the set of all the primes, those are bad ones, for which in the special fiber the covering ceases to be a tau, you can take S prime to be the set of all primes dividing that discriminant, and that's enough, once you've inverted those, to ensure that the covering is a tau on all the special fibers as well as the generic fiber. So this is a tau as a covering, so as a covering of schemes over the spectrum of OK S prime. Okay?
So this is really as small as tilde.
This is really, yeah, now I'm still over K. I haven't yet had to pass to L, to a finite extension. Okay, but now we use the basic fact of that if we now look at, so in particular, if we look at, for all points P in, let's see, what I'm going X to Y. So Y of OKS prime. I can look at the fiber, the scheme theoretic fiber of pi over the point P, which means, you just sort of, in concrete terms, you take this point P and you look at the inverse image, you get a bunch of points in X, and you look at the field of definition, essentially, the coordinate ring of this bunch of points, and that's this fiber. So it's a finite flat algebra over spec O, but the fact that this covering is a tau over spec OKS prime ensures that this fiber is also a tau. So in particular, for all P, the fiber pi star of P is an a tau OKS prime algebra. Hence, it belongs to SHA of OKS prime D, where D is the degree of pi. But now we saw from this the theorem of R's as R ranges over SHA OKS prime D. Okay, and this is finite, so this is a finite extension. L over K is finite by Hermite, and that's the key point in the proof. Okay, so, and now let me just finish with a key corollary of this, of the proof of this theorem. What is it?
What is pi star P supposed to be?
Pi star P. Yeah, this is fiber. Okay, so, yes. Right, so, I mean, it's the coordinate ring. I mean, if you think geometrically, it's the coordinate of the the coordinate ring of the fiber, right? The scheme theoretic fiber. So it's the fiber is spec of that algebra. Okay.
Okay, so pi star P is supposed to be the coordinate ring.
Yeah. Yeah. I mean, this case, right? I mean, yeah. Okay. I mean.
So when you say frac R,
Yeah. Or if you want, I mean, yeah. If I want to be consistent in my terminology, I guess, and kind of stick to this geometric. On this day is spec of, right? An a tau. Okay, that's. If you,
we're taking the quotients of R.
yes. Yeah. Yeah. Here I'm just taking the fraction field. Yeah. Good point. Yes, because I didn't say that these fibers, of course, need not be fields.
Right.
They could be I mean, the generic fiber, they could be products of fields. So I'm taking the total ring of fractions. Yeah. Okay, so finally, let me just state a consequence. Maybe I'll write right here because I'm almost done. So it's a sort of a kind of elementary result, which maybe, at least in my mind, makes the Mordell conjecture, which was proved by Faltings, a little bit believable, or maybe kind of explains why there's a kind of a clear distinction between curves of a genus greater or equal to 2 and curves of a genus 1. And so that's the following corollary. Okay, So before I say the corollary, I need to make a definition. So I say that x, like the curve x, is Mordelic if it satisfies Mordel's conjecture in the sense that x of OLS is finite for all finite extensions of K and for all S finite set of places of L. So if it satisfies the condition of this Siegel faulting sphere, which I stated earlier, that sort of it has finite many cylindrical points for all finite extensions, then I say that the variety, or in this case the curve, is Mordelic. Mordelic means because it satisfies Mordel's conjecture. And the corollary of what I said before is that if two curves are related by an unramified covering, then one is Mordelic if and only if the other is. So then x is Mordelic if and only if y is Mordelic. And that's an interesting statement because you see when two curves are related by an unramified covering, if the curve y has genus greater or equal to, strictly greater or equal to 2, then the genus of x could be much bigger. You'll see an example in the exercises, and it's an easy consequence of the Riemann-Hurwitz formula. So the genus could go up. And so, of course, the interesting implication is the one where you go from this one, right? So where you deduce that y is Mordelic, assuming that x is Mordelic. And this follows from the fact that, so if I want to study y of OLS, or y of OKS. Well, no, what I'm saying in my corollary is that both are equivalent. And I'm saying that the interesting implication is this one. Yeah, I think this is right, the way I stated it.
I'm just questioning your definition of interesting, I guess.
Exactly. Yeah, there's one which is completely trivial.
Right.
Again, this is the interesting one. Okay, so I'll explain why, and then we can see if you still disagree with me. So you take y of OKS, okay? Now, so in other words, what I'm trying to do now is show that y is Mordelic, so that y has finitely many S integral points over any finite extension K, right? So how do I prove this? Well, by my previous result, I know that this is contained in pi of x of O, L, S prime for some finite extension, L of K, and some finite set S prime containing S. Now, by assumption, x is Mordelic, so this is finite, therefore this is finite. Okay, this implication should be trivial. Okay, why is that? Well, it's maybe easier to see by when you look at the contrapositive. If x is not Mordelic, then y is not Mordelic. Because if x is not Mordelic, there exists some finite extension where I have infinitely many rational points, and then mapping them down by pi, I'm going to get infinitely many rational points anymore. So, and in fact, you see, this boring direction doesn't use the fact that pi is unramified. This one does. This is sort of the beef. Okay, so that's basically where I want to leave you with. So it's the idea that when curves are related by certain coverings, unramified ones, or unramified correspondences, the questions concerning the Mordel conjecture or rational points and so on are not at all unrelated. That's going to be actually an important theme of my lectures. So I'm going to finish now. I apologize for running a bit over time with a board of exercises. Those of you who want to work on the exercise session in the evening, you can take down these exercises. These are good things to think about, which are applications of the results that I explained in these lectures, in this first lecture. And this afternoon, there's going to be a lecture by, actually, I'm going to say this, let me just mention it here. There's going to be a lecture by Hugo Chapdelaine, which is going to be concerned with an equation which ostensibly falls a little bit outside the realm of curves, namely the so-called generalized Fermat equation, xp plus yq equals e to the r, where the exponents are allowed to be different. So this is a non-homogeneous equation in 3 variables, so it looks a bit like a surface. In fact, it is a surface. But Hugo is going to explain how the kind of basic notions that I introduced in today's lecture can be used somehow to study this equation. Okay, so that's going to be in Chapdelaine's lecture, which is this afternoon. And so this is sort of like in some sense, the most basic notions. So we'll be using these notions throughout the series of lectures, particularly tomorrow and on Wednesday when I talk about the proof of faultings. Yes?
So in number 2, is that simply show that x of O divided by n times x of O is not integrated?
Exactly, yes. So I take... No. This is an integer. I'm sorry. N is just some. Well, I mean, I guess n greater or equal to 1. Okay. So it's the weak Mordell-Weil theorem in this setting. Okay. So what I'm claiming really is that the ideas that I've explained today, particularly this last lemma on unramified coverings, is what you need to prove the weak Mordell-Weil theorem. Those of you who've never seen the proof of the weak Mordell-Weil theorem, this is a very good exercise. And maybe I should say that also, particularly for part 1, you might need, well, I don't know, depending on how clever you are. I mean, if you're stuck, then ask people who are more experienced. But in principle, what I told you today is enough to really tackle these questions. I mean, the last one, you might need to know some facts like, basic facts like Riemann-Hurwitz and so on. Again, I mean, if you feel that you need to know something to tackle these questions, ask me or someone in the audience who knows a bit more.